Okay, so good day. Welcome to this video. Here we will be solving exam 2, our last exam in analytic geometry, all about our circles. Okay, so let me start with exam question number 1. This is a 3-point question. We have the given circle quantity of x minus 3 squared plus y minus 3 squared equal to 36. You're tasked to choose which of the following statements best describes the lines 1 to 4 below. Now we have these lines y equal to x, y equal to negative x over 2 plus 15, and y equal to 9, and lastly y equal to x minus 6 square root of 2. We have a lot of choices here, and basically it's just asking which among them are the correct tangents to the circle. We have a claim here that only the second line is the tangent to the circle, and so on. Now, it's best that we tackle this problem graphically. We can start this by making some graphical interpretations of the problem. So with that, let me create a graph of what I understand based from the question. So here I know that the circle is given by this equation right here, this one. So let's just perhaps do that. I think we can do this by graphing like this. So let me just get accustomed to this tool. I haven't really used OneNote before, so it may be a bit a learning curve for me right now. So but let's just graph this. We have here x minus 3 squared plus y minus 3 squared equal to 36. So with this case, I know that the radius is just the square root of 36, which is 6. We cannot use the negative value because this is the radius, and the radius is a measure of length. Now, from this statement right here, I know that the center lies in h and k given by these values. In this case, we have negative values here, so h must be the opposite sign of that. So you have positive 3 and k is equals to positive 3 also. So therefore, this circle has a center at positive 3, positive 3. So it's in the first quadrant. So we will graph that here. So this is the center, and then since the radius is 6, we have this. So let's just count 3 units here. So this will be 1, 2, 3 below, and then another 3 units right here, somewhere around there, and maybe there, and also somewhere around here and somewhere around here. Now I'm gonna make a very crude circle right here. I'm not sure of how will I draw this beautifully, but I hope you get my point. Okay, so let me just do this again. So this will be our circle. Now let's start with inspecting the line number 1. We have line number 1 is given by y equal to x. Now when we say y equal to x, it's just a graph of a diagonal line where every x and y coordinates are equal to each other. So for example, we have the point 1, 1, 1, 2, 2, 3, 3, and the same for the negative numbers. Now if you graph that, you will find out that the graph of that line is this. It's just the graph. So let me change the color first. So the first point is 1, 1, again because y equal to x. So every coordinate must have the same numbers for the x and y coordinates. So we have here 1, 1, 2, 2, and so on. Now it must pass through 3, 3, which is our center, which we got this the value. This is the value that we got earlier right here. So again, it should pass through that line because again it has this one of the coordinates or coordinate points inside that given line y equal to x. So in that case, this line is automatically not a tangent of the circle. The reason is that it intersects the circle more than once. As you can see here, there's this point of intersection, another one here. Okay, now I think that's it for the line 1. Now let's examine line number 3 perhaps. Okay, let's skip over some. Let me just make some important points here. Line number 3, we have y equal to 9. Now let's examine this one. When we say y equal to some constant, y equals to some constant, we know that this is a horizontal line. Okay, horizontal. As long as it's y equal to some number. In this case, y is equals to 9. Now if you look at this, the way we graph this is just by looking at where we can plot this horizontal line in the y-axis. In this case, its height from the origin must be 9 units. But if you look at this, we have here 3 as our center, no, sorry, 3, 3. And then from that, we need 6 units upwards, okay, to reach 9. But think about it. In order to reach those 6 units, you have to travel the whole length of the radius. Remember that our radius is 6. Now, at this point right here, the one directly above the center, must be located at the same x coordinate since we are not moving horizontally. But again, this is the center plus radius, so that should be 3 units plus 6 units. That will become 9. Now, coincidentally, when we graph y equal to 9, it should pass through this point at a perfectly horizontal level. Now, my drawing might suggest differently, but this one right here must be perfectly horizontal right there. So y is equal to 9 must intersect the circle at a single point only. In this case, this line right here is a tangent. Okay, this is a tangent. Now, what does this mean is that we are now going to choose which among the choices now involves y equal to 3. Again, this is a part of our deduction. So here, both choices A and B doesn't contain the line 3. So therefore, we can reject the choices A and B. All we have to choose from now is these two choices here, or two statements right here. We have here that both lines 3 and 4 are tangents to the circle, and maybe it could be that there's only a single tangent line here among the choices, or the choice of lines. So we have to validate that one. Okay, so now let's validate the choice letter C. It says here maybe the line 4 is also a tangent to the circle. Now, in order for this to be a tangent to the circle, again, it must pass through, or it must intersect with the circle at most a single point only. So in order to verify that, we can graph this line. Okay, now in order to graph this line number 4 right here, in order to graph this one, we need to look for its values, or the important characteristics of this one. So in this case, we have y equal to x minus 6 square root of 2. Let me just perhaps take it outside right there. And then let's see, what can you find here? We know that the slope, this one, is 1. Remember, this line is in the form of a slope-intercept equation. So in this case, it follows the format of y equals to mx plus b. Here, we have 1 as our slope. So the slope must be 1. It means that for every change in x, there is a positive 1 unit change in y. So we will see that later on when we graph this line. Okay, now let's look at this. We have here negative 6 square root of 2. Okay, that is now our y-intercept, symbolized by the letter b. Okay, negative 6 square root of 2. Now we can perhaps just look at this. Maybe we can grab a calculator. So let me grab a calculator right here, so that we can see its its decimal value. So there's a calculator right here. Let me check. So we have here negative 6 square root of 2. So that is negative 8.485. So let's just estimate that to be equal to, okay, let me take this one outside. Okay, so let me draw again. So this is around the value. Let me change that to a congruent sign. Oh, sorry, it's an approximate sign. This will be approximately equal to 8.485. Okay, let's round that value there. Now, if you graph this, you would have to count here negative 8 units below. So we have 3 right here. So let's just perhaps estimate this to be somewhere around here. Okay, now, so maybe this is now our negative 6 square root of 2. Okay, this is just an estimate. Our drawing is not really accurate. Now, let's try to draw a line. So in this case, we know that the slope is equal to 1, given by this value right here, right there. Now, since that is the case, again, as what I've stated earlier, when the slope is 1, it means that for every change in x, there is a corresponding equal change in y. Equal in the sense that 1 unit change in x is also 1 unit change in y. Okay? So in this case, moving from this point, right here from the y-intercept, let's move 1 units to the right, so it could be somewhere around here. And then what does this mean is that since the slope is 1, the next point must be 1 units higher than this. Okay, so like somewhere around here. We can extend this idea further. So perhaps another 1 unit to the x, and then 1 unit upwards right here. So now if you connect this line, you connect these 3 lines that 3 points that I made so far, you'll see that it has a tendency to be a tangent to this circle. Okay, my drawing is not perfect, so please just bear with me in this one. In this case, my drawing is a bit very bad. It's not actually a bit, but it's very bad right now. It has the tendency to be a tangent, but maybe it's just my drawing that is screwing up this illustration. So let's verify now, maybe analytically, in order to verify whether this is actually a tangent or not. Again, we have seen that there could be a chance that this is a tangent, because again, this could just be attributed to the drawing errors that I did. Maybe the real line doesn't pass through this line at all. Maybe it's just an exact tangent at this point right there. So I'm not really sure at this point. So the way to deal with that analytically is to find the intersection, or whether to check whether the lines have an intersection with the circle. Okay, so we have to verify intersection. Verify the existence of intersections between the circle and the line. Again, we have the circle given by the equation x minus 3. Okay, sorry for that. I'm really just learning now how to use this app. I haven't really used OneNote before, so we have this again. Let me continue. This is x minus 3 squared plus 1 minus 3 squared is equals to 36. And now, the line that we want to test is again the same line as above. Again, this is a repeat. Now, if you're confident that your drawing is fairly accurate and you believe that is a tangent line, then maybe you could decide from that. But if you really want to be sure, then do this method. Okay. In this case, I'm doing this because I'm not really sure if my drawing is accurate enough to verify whether this is not a tangent or maybe this is a tangent. Again, my thoughts is that maybe this could be a tangent because it lies very close to the tip of this circle, or on the edges of the circle. So now let me write again the equation of the line. We have this y equal to x minus 6 square root of 2. Now let's go down. Let's try to think about this analytically. Okay. Now, in order to find the intersections of this circle right here, okay, let me grab another pen. Okay. In order to find the intersection of this circle and this line, we just have to substitute this equation into each other. Okay, and the most convenient way to do that is maybe substitute the equation of the line in terms of y to the equation of the circle, since we have isolated y already. Okay, in this case, let me grab the equation of the circle. I have a x minus 3 squared and then plus y. Now, in this case, let's replace y with the contents of the line. Again, this y right here, we will replace this with the contents of this line right here. Okay, so this will now become x minus 6 square root of 2 minus 3. And then you square that one. That will become, okay, it will become 36. Now, I should have put here a parenthesis, opening and closing parenthesis encompassing this value of substitution. But then again, since this is the first term, this parenthesis can just be taken apart. Okay, so I hope you take note of that. In other cases, it's always safe to put a parenthesis whenever you substitute. Okay, now let's expand this binomials right here. Basically, we have a binomial and a trinomial, but since these two terms right here are pure numbers, we can treat them as binomials. But in this case, let's just expand this one. So let's have here x squared plus, sorry, this will become 6x plus 9. Again, this is using the fold method or your binomial expansion. Now in this case, this could be a bit trivial, but for me, let us use now. We can use here the what do you call this? We can use here just we can do this by just treating these two terms right here as a single term. We can expand this using the trinomial way, but I find that it's a lot easier if you treat this term. Okay, let me write this one. X minus 6 square root of 2 minus 3 squared. It's best to treat this one as a somewhat kind of a binomial. In this case, let me isolate these two constants here. Like this now. Okay. Now, if you look at this way, notice this look like a binomial. Since 6 square root of 2 plus 3 are like terms, they're both constants. So, doing that, we can just use the binomial expansion. In this case, it will become x squared minus 2x. Sorry, let me copy this term right here, twice of this. So now have 6 square root of 2 plus 3, and then x, and then lastly we have this square root 6 square root of 2 plus 3, and then you square that one, and then we have 36. Okay, now let us simplify whatever we can. So we now have x squared and x squared. So you now have 2x squared, and then we have here 6x minus 2, this one. So let me just write this one. This will become negative, and then let me just turn this into positive 6 plus 2 parenthesis again, and then we have here 6 square root of 2 plus 3, and then lastly x. And then for the constants, we now have let's see, this will become 9 plus 6 square root of 2 plus 3 squared minus 36 equal to 0. Now, for simplicity, we can use the binomial theorem right here. The quadratic equation right here. Remember, in order to solve for x in here, we can use the formula x is equals to negative b plus minus 4, square root of b squared minus 4ac divided by 2a. Now in this case, we can let some values, or we can assign some values in order to quickly remember what are those. In this case, this is the first term besides x squared, so that we will call that a. That is equal to 2. And in this case, we have b, the second term coefficient. In this case, the coefficient of x. In this case, it's a negative value, negative of the quantity 6 plus 2 times 6 square root of 2. In fact, in this case, we have this. We can put a square bracket here for emphasis. This will become negative 6 . Okay, this will become 6 plus 2 times 6 square root of 2 plus 3. Okay, so we have this coefficient now. Now for letter C, we can write this as just the sum of this values right here. 9 plus 6 square root of 2 plus 3 squared minus 36. Now, what we will do is to either simplify this and plug this all in. But what I find is it's much easier if you just use your calculator to do the job. Okay? So in this case, let me grab on our calculator right here. And I don't know if you learned this already, but we can use the storage. We can store variables in our calculator. In this case, let me store 2 in a variable a. So what I'm gonna do is that I'm just gonna type 2 here, press equal, and again the next step will be shift, and then wherever you can see the symbol STO, that means store. So I'm gonna go and shift again. I press shift here. Notice it highlighted there. Shift store, and then I'm gonna select the variable that I want, what variable where I want 2 to be located at. In this case, I want 2 to be stored at a for easier collection later on. So let's store this in variable a. So again, I pressed and shift store. So notice STO has been highlighted here. So I'm gonna press now the variable a. So ans, or the answer, will now be stored at variable a. So press equals, and we have this. I don't think you have to press equals actually. So if I want to recall the value of a, I'm just gonna say alpha of a, and then if you look at this, equal sign will result to the value of 2. Now in the same manner, let's have this negative 6 plus 2 times the quantity of 6 square root of 2 plus 3. Okay, that's it. And then let's store this at shift store and then letter B. And then for the last value we have here 9 plus 6 square root of 2 plus 3 squared minus 36. And we have that answer right there. So now let's store that in the variable C. Now doing this, remember we have this statement right here. We have this statement. So we can just plug in those values now using our calculators. Let me grab again the calculator right here. There is a very easy method to do this. We can either do this and type all of this. We can now write negative alpha b, and then we can choose either, okay, sorry, let's say become alpha b, and we can just here to either use plus or minus for the first case and second case. So we can here right here square root of alpha b squared minus 4ac over 2 times a. Now we can take the answer here and do that. But there's a lot more easier way to do this kind of operations. In fact, it's a built-in method. Now if you look at this, we can go into the equation mode, number 5. And let's look at number 3. That is the quadratic equation. Again, we have a quadratic equation, 2x squared, and then some x value, and then some constant. So that is number 3 right there. And then we have this a, b, and c panels right there. Now, what I will do is just recall the values. So alpha a, and then equals, and then alpha b, and then equals, and then alpha c, and then equals. So what it will give us now are the two roots of this equation. Again, the advantage of this is we don't have to type everything here for the plus minus case. So remember, we need to do this twice in order to take the both of the cases. In this case, it's automatically done for us. Now let's look at the answers for this one. These are the roots of the quadratic equation. So let's write here x1, the first root. That is, let me grab the calculator again. It is 3 plus 3 square root of 2. So, okay. It's 3 plus 3 square root of 2. Now for the second case, let me grab again the calculator and then press the equal sign twice. Okay, so as you can see here, it doesn't return any further values anymore. So it means that the two roots are equal. Notice this doesn't give a value of x2 or another x. In this case, it just says x value minimum, or the minimum value for x. In this case, we don't have any more values. The usual case here is that we get two values for x. In this case, it doesn't give us any more other than the first one. So it means that the second one must be equal to the first one. Now, what does this mean? Okay. Here, x1 and x2 are equal. So it means that they correspond at the same point. Notice here that if the return value there, or for x1 and x2 are not the same, this could be those two values right here. Whatever is the x coordinate here and whatever is the x coordinate here. But since these two are equal, again, from the results of the calculator, since those two are equal, what it indicates is that they are the same. So x1 and x2 must correspond to the same x position. In this case, it corresponds to the same point. In this case, now, it indicates that the intersection between your circle and the line is only at a single point. So therefore, this graph is incorrect. The real graph of our circle now must intersect with this line at only that given point. Again, that is when x1 or even x2, or in this case, let's just call it x. It's when x is equal to 3 plus 3 square root of 2. Okay, so now what it is saying to us is that this line right here is also a tangent. Okay, so in this case, y equal to 9 is a tangent line, and y is equals to x minus 6 square root of 2 is also a tangent line to the circle. Now in this case, the answer must be letter C. Okay, it's that 1 and 3 and 4 rather must be tangents to the circle. Okay, sorry for that. I'm trying to get the highlighter so that I can highlight the answer. So in this case, this is the answer. 3 and 4 are the tangents to the circle. Okay, so I guess that's it for number 1. Okay, now let's move on to number 2. Okay, so for number 2, again, let me just perhaps grab another screenshot of that one, and I'm gonna put it below. So right here, so wait a minute, let me take a screenshot of number 2 and copy it here. Okay. Okay, so it's haven't the screenshot was not showing up, so let me okay, right there. Okay, so for number 2, if the point 3, negative 2 lies in the circle, the center at negative is at negative 1, 1, and the equation of the circle is given by which of among the choices below. Now, this problem is a lot simpler than the previous one, hence the 2 points. So if you look at this, we can do this easily by graphing the known points. Okay, so in this case, let me graph the given points. So let me create the xy plane here. Okay, so it's a lot slanted than I want to. So right there, we can plot these points right there. Okay, now let's plot the point 3, negative 2. So it could be located here. So let's just count here. 1, 2, and 3. And then negative 2 should be below the origin. So in this case, that is this point. Now also, we have the center at negative 1, 1. So in this case, the center is located in here. Negative 1, 1. Right there. So let me color that differently to indicate that that is our center. Okay, so it's not a different color. In fact, let me color this. Okay, this point right here differently. Okay, now this is our center, and this is a point in the circle. It means that this circle now must be shaped like this. Okay, so again, forgive my drawing, it's not really perfect. I cannot really draw a perfect circle. I don't have the skills for that, but let me just approximate this with all my might. Okay, so it could be this circle right there. Now what this tells us is that we have the ability now to measure our radius. Our radius is just the distance connecting the center and any points within our circle. And luckily, we have this single point again. Let me just label this to be 3, negative 2. And this one will be negative 1, 1. This is our radius. Now, in order to figure out what the radius is, we just need to use the distance formula for these points. Remember that our distance formula is just given by x sub 1 minus x sub 2 squared plus y sub 1 minus y sub 2 squared. Okay, now in this case, let's call this perhaps point 1, and let's call this point 2. Again, the choice is arbitrary. You can choose any of them to be point 1 and point 2. Since we are squaring the terms, it doesn't really matter. Okay, so let's solve now for the distance. In this case, our distance is just our radius. Okay, in this case now, let's put the square root. So this is 0.1. So the x there is negative 1. And then minus x here is 3. So that will become minus 3 squared. And then right here we have y sub 1. That is positive 1. minus of the negative, 1 minus negative 2. So minus a negative number that becomes a positive number instead. So that will become 1 plus 2 right here. Okay, and then not forget the squared of a sign. Okay, now let's proceed. This will now become, again, this is negative 1, negative 3. So that is negative 4 squared. That will become 16. And then this will become 1 plus 2. That is 3 squared. That will become positive 9. In this case now, our radius will be the square root of 16 plus 9. So this will become 25, I believe so. Okay, this will have, excuse me. Okay, so we have now r is equals to 25. So, sorry, r is equals to square root of 25. So now r must be 5. That is the square root of r 25. Okay, that is the radius of our circle. Now, all we need to do, since we have our radius and we have our center, is just to construct this standard form for our circle. Remember, the standard form for our circle is given by the equation x minus h squared plus y minus k squared is equals to r squared. In this case, I know that the center is located at negative 1, 1. So it means that my hk values is at negative 1 and 1 respectively. So now we construct this standard form. This will become x minus a negative number, that is negative 1. So this becomes positive 1. And then we have here y minus 1 squared. And then our r is 5. So that will become 5 squared. Okay. Now, since these choices right here are given in general format, we have to transform the standard form into the expanded notation. In this case, we're referring to the general form again. So in this case, I'm just going to use the FOIL method, or the binomial expansion, for each of the binomials here. So now this will become x squared plus 2x plus 1, and then the other one will become plus y squared minus 2y plus 1 is equals to 25. Now, I'm just going to rearrange the terms according to the preferred method of arrangement. Again, the choice of arrangement here is arbitrary. It's just depending on how we define the general form of equations for conic sections. In this case, we want the squared terms to be first. We need x to follow. We need y to follow. That is negative 2y. And then we combine all of the constants. In this case, we have here 1 plus 1. And remember, this will become negative 25. So now, 2 minus 25, that will become negative 23 equal to 0. So we look for the choices. We look at negative 23 and see if whether it matches the rest of the terms. So we have now negative 2y, positive 2x, and both x squared and y squared are positive. So in this case, this will now be the correct answer for question number 2. Okay? So I guess that's it for question number 2. Okay, now let's move on to question number 3. And again, let me just take a screenshot of the question. Okay. Okay, for question number 3. When a circle represented by the equation x squared plus y squared is equal to 25 is shifted 3 units horizontally to the right and 2 units vertically down, it coincides with which circle below? Again, this problem is a lot easier also. We just need to look at where the center will now be located at after the Z transformation. In this case, it's a translation. Okay. Now, let's look at the first equation, or the original equation. We have here x squared plus y squared is equal to 25. The information that we can get here is the center's the circle's original center and the radius. In this case, the center is just at 0, 0. It means that the circle is has its center at the origin. Again, because we don't have any more terms attached to our x and y. Now, if you don't want the explanation, maybe it would be clear if you just write this way. Right? You can write it this way, and you will see now that, again, these two the equations are the same, are equivalent to each other. It's just that we want to show that h and k are both equal to 0. Okay, so it means that our starting point is at the origin. Now our radius must now be equal to the square root of 25 or just 5. Okay, so in this case, we know that we are not touching the radius. When we move the center, it's basically just the same size of a circle. It's just the center is located at a different position. In this case, let's examine this one. So we want the center to be moved 3 units horizontally. Okay, so let's have this new center represented by h and k again. So our new center now will be 3 units horizontally from the starting point. So again, we have 0 as our starting point, 3 units horizontally to the right. So that means that our x coordinate will go to the positive x-axis. In this case, we add 3 units. Positive 3 units again because it's towards the right. And for k, our y coordinate for the center, we start at 0 and then move 2 units vertically downwards. So since it's downwards, we need to move by adding negative 2 units to the starting value. In this case now, our center is therefore located at 3, negative 2. But since our radius is still the same, we haven't changed the size of our circle, we can now construct the standard form of this new circle. In this case, the new location would suggest that the standard form should be at x minus 3 squared. Again, minus 3 because this is positive. And then y plus 2 because this one is a negative value, and then squared. And then r squared, that is 25 still. Okay, now let us convert this to the general form by expanding each of the binomials present here. In this case, the first binomial will be expanded to x squared minus 6x plus 9 plus y squared plus 4y plus 4. Okay, let me erase my 4 here. It looks like a very close symbol to 9. Yeah, again, it's not my fault. I either a bad penmanship or I'm not really used to OneNote. Okay, so much for the alibis. Let's continue. We have now this. Okay, again, rearrange according to the general format. We have here x squared plus y squared, and then follows 6, minus 6x, and then 4y. And then let's combine all of the remaining constants. We have here 9 plus 4. Sorry, that is, again, let me check. So that is 9. Okay, let me change the mode. 9 plus 4 minus 25. Okay, again, minus 25 because if we transpose 25 to the left hand side, it will become a negative value. So here we have minus 12 instead. Okay, so that's the general form for that circle. Now, comparing this to our choices, we just look at the values which are the same. So in this case, it is, I believe, choice letter B. That is x squared plus y squared minus 6x plus 4y minus 12. So therefore, the answer for this question is this letter right here. Okay, I hope it's clear. Okay, now, so I guess that's it. We are done with question number 3. Now for question number 4, let's proceed again. Let me take again another screenshot of this. Okay, for question number 4, which of the following circle represents the circle which is only or completely located at the first quadrant? Okay, when we say completely located in the first quadrant or completely in the first quadrant, it means that the circle must not cross the first quadrant. So in this case, let me draw our Cartesian plane. Right, we can still remember what those quadrants mean. Okay, so if you look at this, we have here this one, and this one right here. Okay. Again, this quadrant right here, this corner right here, is called quadrant 1. So I don't know if I can grab on some highlighters here, or I don't know. I will. I don't know if it's really a good idea to highlight all of these things, but let me, for emphasis, highlight that this is Q1. Okay, all values right here is located at quadrant 1. Now, similarly, I'm not gonna color anymore for the rest of the quadrants. We call this quadrant 2 and quadrant 3 and quadrant 4. They can also use the the Roman numerals, but for that, in this case, we're just using plain numbers. Anyway, these are just symbols. So they should mean the same thing. But again, remember, this quadrant right here is quadrant 1. The second here is quadrant 2, and quadrant 3 right here, and quadrant 4 for that. So let me erase those quadrant labels. Let's continue with the problem. Okay, according to the problem, we want the circle to be completely located inside this region right here. We don't want any circle like this, or we don't want any circle that is completely outside of the said quadrant. We don't want any circle crossing the other quadrants right there. So those are all invalid. You only need this first case right here. The circle should be completely located at the first quadrant. Let us examine. In this case right here, this C and D seems a bit suspicious for me. Why? Because if you look at this, their centers are not located at the first quadrant. How do I say so? In this case, let's examine here. I know that the center's H value is -1 and its K value is at -12. So obviously that's a negative number. So let's say this is -10 and perhaps this is -12. The center is located here. So it means that the circle is now impossible to be within the first quadrant, since again the center is at the quadrant 3. In this case now, let's move on and illustrate again why this seems a bit suspicious. If you look at this, the H coordinate is at -6 and the K coordinate is at +9. So in this case, it could be around here, -6 and +9. So it should be a lot shorter, or less shorter than the -10 value. So right here. So the center now of that circle is at quadrant 2. So therefore, those two are automatically disqualified from our choices. Now let's move on to A and B. Now this both A and B right here seems a bit convincing, because if you look at this, for A, the center is located at, if you guess it right, it's at +8 and its K value is at +9. While for the second one, its H value is at +10 and K value is at +7. So let's focus now first for letter A. Let's try to graph that one. We know that the radius of that is the square root of 100. Square root of 100, that's our radius. For here, that is square root of 36. So in this case, the first circle must have a radius of 10, and then the second circle, okay, and then second circle must have a radius of 6. Now, if you look at this, you might have already an idea on what does this mean, but if it's not clear yet, let us graph this first circle, letter A. So it's located at +8, 9. So it's perhaps right here, 8 and 9, right there. So it's good. Its center is at the first quadrant. Now for the second circle, let's graph here the center that is located at 10, 7. So that's in this case, it's around about 2 units here, and then 7 is somewhere around right here. Okay, so I'm really just guessing up to this point right there. Again, so let me say that this is 7 and this is 10 and this is 8 and this is 9. So it's not really up to scale, but bear with me. Okay, now, so let's have this first circle, okay, or the previous circle that we had, letter A. Now it says here that the radius is 10. So starting from the center 8, 9, the circle will have a point 10 units far away from the center. So in this case, we know that from 9, we need to move 10 units below to find a point right here. So from 9, 10 units below, that is 9 minus 10 or negative 1. So we will find out now that this circle has a point that crossed our quadrant 1. So now this circle is disqualified now to be within the criteria that we need. Because this circle is probably shaped this way. Again, my drawing is really bad. It's not even a center. You cannot call that a center. Okay, so again, please bear with me for this one. Okay, so there's no point in redrawing that one. It cannot be mitigated anymore. So let's proceed. Now, I hope it's clear now that the remaining circle that is represented by B is probably the best candidate here. If not, then we don't have a choice among these given choices right here. So it says that the farthest point must be 6 units away from the center. Okay, starting from 7, 6 units below would mean 7 minus 6, or that is positive 1. So in this case, one of the farthest point of that circle must be located here. Now if you graph this one, this would be the said circle. Again, my graph is very, very bad, so therefore it's not really accurate if you graph this in an actual app such as GeoGebra. In this case, this is the circle that we want, completely in the first quadrant, or Q1. Okay, I can write it also by Roman numerals, Q1, QI. Okay, in this case, that is our answer. So the answer for that question, again, to emphasize, that is letter B. Okay, I guess that's it for this question. Now for question number 5. Okay, let's move on to question number 5. In this case, it doesn't require us to solve that much. It's just a matter of analysis. Okay, for question number 5, let me take again a screenshot right here. I'm just copying this screenshot right there, and let me paste it here. Okay, so we have this. Given 2 fixed points, how many circles can be made to pass through the said points simultaneously? Okay, given 2 fixed points, so it could be any random points in the Cartesian plane. So in this case, we will do that. Let's create 2 random points, or let's make 2 random points within the Cartesian plane. So I'm not really sure if I can further extend this. Okay, so I can. But first, let me try to grab on some new pen. Okay. Okay, in this case, let me make those 2 random fixed points. It doesn't say any location, so it could be any points as long as those are 2 points on the Cartesian plane. Okay, now, given 2 points, how many circles can be made to pass through the said points simultaneously? We have an option that says 1, 2, 3, and the last one says it could be infinitely many circles. Now, what you have to remember is that when we have 2 points where we want our circle to pass through, it doesn't really mean that that is the location of the endpoints of our diameter. Okay, we can draw a circle right here. Okay, again, my drawing would really be bad for this kind of situation, or any situation, but just bear with me in this one. We could have this circle. These 2 points right here corresponds to the diameter, but then it doesn't really require us that this circle is the only circle that we can make. Again, this is the case where these 2 points are the diameter of our circle. Okay, so I'm giving up on that. But remember, there could be cases where those 2 points are not our diameter. Those are the chords of our circle. It could be this way, right? Or even we could have another circle this way. Again, its goal is just to pass through the said points. Now, if that's the case, it looks like we have a lot of options. Okay? We could say 2, 3, or we could even say infinitely many. Now, the strongest argument that we could make is probably to remember some of the properties of our chords. It says here that we have some property of our chords that we need to remember. I believe we have discussed this one, but again, if you have 2 points or 2 points corresponding to the endpoints of a chord, the perpendicular bisector of that chord would contain the center of our circle. So in this case, okay, so I'm not really drawing this one, but let me have this as the perpendicular bisector. Okay, this is our perpendicular bisector for the points, for the given points. So let's call this point A and point B perhaps, and this is our perpendicular bisector right there. Okay, so we have this perpendicular bisector A and B. We have this perpendicular bisector colored in blue, and remember what we said during our discussion is that this perpendicular bisector now will contain the center of the circle passing through the said 2 points. Okay, it just says that the center could be located anywhere along that line. Again, the condition that the circle must pass through the said 2 points. Okay, so again, we could draw something like this. We have these 2 points. We have this circle. The center should be located along this line. For any other circle, that must also be true. So let me just draw another crude circle right here. Center must also be located here. Now, if you look at this, since this center is movable along this perpendicular bisector, by movable I mean it could be anywhere along this center, in this perpendicular bisector, it means that there are infinitely possible centers that we could make. When I say infinitely many possible centers, it would also correspond to an infinitely many circles. So this means that the answer must be an infinitely many number of circles that we can make to pass through the points A and B. Okay, now I believe I have given an illustration right here for this problem, and I guess it's best that we grab into that and then show what I mean in a more desirable manner. So let me grab onto this and perhaps put it here. So let me just have a word or two about this one. Okay, in this case, look at these circles now that we are able to draw. Each of those blue dashed circles correspond to all of the possible circles that we can make for such that it follows that it must pass through the points A and B. Now those are just some of the many possible circles right there. Just that the common property of them all is that their center must be located along the perpendicular bisector of the said chord, said line segment connecting A and B. Okay, so that further statements, let's have that answer letter D for question number 5. Okay, that's for question number 5. I guess we are now ready to move on to question number 6, which is a bit related to question number 5. And the only change there is that for question number 6, we are talking about 3 points instead. Instead of a single point, we are talking about 3 points where we want our circle to pass through. Okay, right there. Okay, this is for question number 6. Okay, we have this. Given 3 non-collinear fixed points, how many circles can be made to pass through the said points simultaneously? The same hint is given for the same or related question. And the same choices we have here: A equal to 1, B 2, 3, C, and D could be an infinitely many number of circles. Now let's evaluate each of your choices. Let's have here another drawing. That's perhaps A, B, C. Let's call it A, B, C in this case. A, B, right here, and then maybe C right here. Okay. Now, it says here non-collinear fixed points. Okay, remember, non-collinear, it means that we cannot connect all of the 3 points in a single line. Probably you will see why later on. Okay, Now, if these two are or if these three are non-collinear, we can draw therefore two segments connecting the 3 points. We can either choose any of them, but we can draw two segments right there, or even three if you want. You can draw another three right here, but for this application, I don't think it will be necessary. So, all we need to remember now is that the same property of chords earlier. Remember, when our circle passes through each of these points, this means that the lines we are drawing are chords of that circle. Although my drawing is not really good for this one, but let's just say that maybe this is the circle. Okay, I'm trying to approximate where the circle could be located in this case. So I'm afraid I'm drawing an ellipse instead. So okay, so I'm really butchering this drawing, but it could be this circle. Okay, that's it. Now it could be this circle. Remember, each of these segments now are chords of that circle. Okay, now remembering the said property earlier, it means that the perpendicular of the bisectors must contain the center. In this case, let me create a perpendicular bisector of the segment AB, or the line segment connecting points AB. So this is the said. Okay, so I'd keep pressing that one. So maybe. Okay, this way. Okay. Okay. So I have a perpendicular bisector, or so I want it to be a perpendicular bisector. So just imagine it is a perpendicular bisector instead. And another segment right here, we're gonna draw another perpendicular bisector. So it should pass through the midpoint and be perpendicular to the line segment right there. Okay, now again, we've said that those perpendicular bisector must contain the intersection. Okay, now think about it. If we still go back to the old thinking that this center could be located anywhere along this line, it would really violate the idea that this line right here must also contain the center. In this case, it doesn't contain the center. It's only contained on the other, or in this line that I'm drawing at. So in order to satisfy both of the lines, or the condition that both of the lines must contain the center, the only way possible for that to happen is if the center is located right here. Anywhere else, it would be that only the single line contains the point, and the other line will not contain the point. In that case, it violates with the idea that each line must contain the center. So what this means is that there is only one possible way for us to find a center. It's the intersection of those two perpendicular bisectors. So in this case, if we are given 3 points and we want to let a circle pass through each of the 3 points, then there is only a single possible circle for that. So the answer of this question is obviously letter A. Okay, that is, only one circle is allowed to be made in that condition. Now, you might wonder what will happen if the 3 points are collinear. So in this case, if the 3 points are collinear, they should have, or they should be in the same line. So I'm gonna draw here a line, perhaps like this, and let's call this point A, let's call this point B, and perhaps this point C. Okay, these are all collinear. Now, if these 3 points are in a circle, we can again draw another set of line segments that corresponds to the chords of the circle. Okay, excuse me. So line segments that corresponds to the chords of a circle. Okay, in that case, I can draw another perpendicular bisector here and another perpendicular bisector here. Okay, using the same property as earlier. But what you'll find out that in this case, our two perpendicular bisectors will have the same slopes. It means that they are parallel and will never intersect. And if that's the case, if they never intersect, we cannot create this point right here. At least we cannot find that point right there. So it means that there is no possible circle that can be created if the given 3 points are collinear. Okay, so that's the argument right there. But again, for this problem, the answer is letter A. So I guess we are done with that. So we can now move on to the next question, for question number 7. So let me grab again the question for question number 7. Okay, for question number 7, how many tangent lines into a circle can be made if each of the said lines must pass through a certain point outside of our circle? So let's draw a circle. Let's try to draw a circle. So I have a circle right here. Now, how many tangent lines there can we make for that circle such that we require each of the tangent line must pass through a given random point outside the circle? And if you really try to figure this out by observation, it can be done easily. Perhaps we can draw a tangent line right here that starts at this point. Okay, like this. And passes through the circle only once at a specific point right here. Although that's not really a line, I'm just really approximating in that case. Okay, we can draw that. But what are the other points or other certain lines, tangent lines that we can draw? We cannot draw any more along this side, because if we do so, we will intersect now these points nearer to the given fixed point outside. In this case, if we draw another tangent line, like this, we cannot really do that because will have to intersect the circle twice. Now the only option for us is to go in the other direction, and that other direction is this tangent line right here, right there. So now we can only do 2 tangent lines if we require those tangent lines to pass through the point outside of our circle. Okay, now if you pull this point nearer to the circle, it must also change the slope of your tangent lines. In this case, if this is the point here and it's nearer to the center circle, so in this case the tangent line could look like this, lines rather. So again, that is wrong. I'm not really suggesting that they intersect at the same point. So let's change up the point of tangency a bit. So probably this way. Okay. Probably that way. Okay, so this is the point of tangency for each of them. Now, the same holds true is that there are only 2 possible tangent lines for that. The moment that you take the center, the fixed point inside the circle, you cannot really create a tangent line in that manner. Okay? So in that case, the answer is 2. Now, I believe we can prove this analytically, but again, I prefer now, just by looking at this, we can really see why that's the case. An exciting problem might be to prove this analytically, but we will reserve that for the future. Okay, for question number 7, again, the answer is letter C, 2. There are 2 possible tangent lines that we can make in a circle if we want it to pass through a given fixed point outside the circle. Okay, so let's move on to question number 8. So let me grab question number 8 right here. We have this circle again, circle. So we have this given a circle, x squared plus y squared minus 440x minus 46y plus 2022 squared plus 2023 squared minus 2024 squared is equal to 0, and we have to answer the following questions: this location of its center, the radius, and the eccentricity of our circle. Now, right out of the bat, we can answer this question, or question 8.c, the eccentricity of a given circle. I explained this last time. For a circle, the eccentricity is 0. So we are done with this question. Okay, but for the remaining question, we can do this easily. Now, all we need to do really is to rearrange the terms here. In this case, look at this. I will rearrange the terms such that I'll have now the terms with x's, and I'll choose 1 among the constants, and you will see why later on. Why am I doing, or why am I choosing that one to be besides the first group? For the second group, that will be the group of y values, as will become positive y squared minus 46y, and then I will choose positive 2023 for that. And I will transpose negative 2024 squared to the other side. That will become positive 2024 squared. Okay, now, look at this. The way that I rearrange this is because I know that 2022 is just 4044 divided by 2. And I know that 4046 divided by 2 is just 2023. In this case, therefore, we can just say that these two groups right here are already in the perfect square form. In this case, all we need to do is to compress each of them to the binomial form. So this will now become x minus 2022 squared plus y minus 2023 squared is equals to 2024 squared. Okay, now looking at this, we now have an idea where the center is. We know that h is equals to positive 2022 and k is positive 2023. And we know that the radius must be 2024. That is the square root. Again, r squared is 2024 squared. So therefore, r must just be the square root of that. We just get rid of the square root. 2 of r is equals to 2024. Okay? So therefore, we can answer the problems here. We know that the center is located now at HK or 2022, 2023. And that is the choice letter B. Okay, so let me highlight that one. And then we have this. And for letter B or 8 point B, the radius must be 2024 units. So in this case, that is the answer. Okay, I hope you got that one. That is a standard procedure when we are dealing with our circle. It's just a matter of choice now and whether we can see why are we doing this. Anyway, if you do not recognize that these are complete squares, you can do the usual process. You can add half of this 4044 and add half of 4046, and what you will find is that those added terms will just cancel out with the given expressions for positive 2022 squared and positive 2023 squared. Okay, anyway, let's move on. Let's go for question number 9. Okay, let me take question number 9 from the other side. So it says here, okay, so I don't really think, okay, so that's it. That is question number 9. Okay, a circle is described by the equation given there, or the standard form of a circle, where the center is at HK and the center's, okay, the radius is R. Now, if the center's distance from the origin is greater than R, how near is the nearest point in the circle to the origin? Now, this could be, there are a lot of words, so let's draw what does this mean. Okay. Let's focus first on this one. The center's distance from the origin is greater than R. So therefore, the nearest point that the center can make is along another circle that I'm going to draw now. Okay, so let me illustrate this one. Any circle following this problem's idea must have, again, a center that is away from the origin by more than r units. So in this case, this center right here, this possible center right here, must be r units away from the origin. Okay, we could have this circle right there. The center is r units from the origin. So the only other circle that we can make are circles that are further down this way. Okay, we can have another circle right here for the same radius and another circle for the same radius right there. Now, those are a lot of circles, but the point is this is the closest our center could get from the origin. So therefore, anywhere along this zone right here, we cannot draw any centers anymore. All we can draw our center from is from these points outside this inner circle. In this case, we can have this circle right here. Okay, again, as long as its distance is greater than the radius. We can have also a circle that looks like this. It doesn't matter as long as the center is greater than its radius. Okay, its distance from the origin is greater than its radius. Now let's consider the special case of our circle. Maybe for illustrative purposes, let's have this circle right here. Okay, let me erase this one. Okay, sorry, it's just bugging up right now, so I'm not really used to this one, so please bear with me. Okay, so let me erase this. Okay, we have that, and we have this. Okay, another color. Okay, now let's have a point right here. That is our center. Let's call that HK. And again, it says a radius R, so let's have this R right here. Okay, it's an arbitrary radius R. Okay, this R now is a lot shorter than this distance, so this is valid. Okay, that's a requirement there. The distance of our center must always be greater than the radius of our circle. So we can have that. Now, it says here, how near is the nearest point in the circle to the origin? So when we talk about the nearest point, it should be this point right here. Okay, it's asking how near that point is from the origin. Okay, what is the distance from this point down to this point right here? Now, if you look at this, we just need to measure the distance of the center from the origin. Let's call that big R, and subtract the radius here, right? Notice this is just still the radius. So therefore, all we need to do now, in order to find this distance, let me just change some color. This is still R, and let's call this D there here, the distance that we want. It's just given by big R minus small r. Now, what is big R? In this case, big R is just the distance from HK and the origin. Okay, that is from HK to the origin. So therefore, we can use the distance formula. Those are 2 points. Let's call this center point 1 and point 2. Again, the choice is relative, so you can do that. So now I have here h minus 0 squared plus k minus 0 squared. Now if you solve this one, this will become just h squared plus k squared. So therefore, our distance now, again given by r minus r, distance is just equal to the square root of h squared plus k squared minus r. So in this case, our answer now should be among the choices, and it's at letter B right here. Okay, that is letter B. Square root of h squared plus k squared minus r. Not r squared, but just r. Okay, that is for question number 9. I guess we're done with question number 9. Okay, so let's move on to question number 10, the last question for multiple choice. So we have here this one. Okay, for 2 points, evaluate the following statement. A circle is the locus of all points such that all of the distances must be equal to the distance to a given fixed point called the center and a fixed distance called the diameter. Now, let's try to evaluate this one. In a circle, we have a fixed point that is called the center. And at any given point in a circle, its distance from the center must be the same. That is correct. Okay. Any point within a circle must have the same distance from the fixed point. But what do we call that fixed distance? In this case, it should now be evident that fixed distance right there is not the diameter. That is our radius. This is our radius. So therefore, this question now, or this statement now, is false because of the word diameter. So this is the answer. Okay? This is false because the fixed distance is not the diameter, but that is our radius. Again, my drawing is not accurate, but just put it this way. Yeah. Okay? So we are done with question number 10. I guess that's it. We are done with those questions. So I guess we can now move on to the problem solving part. Okay. Let me grab in question number 1 from problem solving. Again, I'm using set A. So for set B, you can just follow along. You have the same questions. All probably you have different choices and arrangement, but those are basically the same questions. Okay, for this one, let me grab this first question. Let me paste it here. Okay, this is the first question for our problem solving. It's 5 points. So let's try to solve this one. Find the shortest distance between the circle x squared plus y squared minus 2x minus 10y plus 9 equal to 0 and the line y is equals to x minus 6. Okay, let's try to figure out how would this look like. Okay, we have a circle perhaps right there, and probably we have a line right here. I don't know yet if that is the case, but what we need here is the shortest distance from the circle and the line. And shortest distance, remember, the shortest distance from this given scenario would always be the distance that follows along this perpendicular line right here. Perpendicular with respect to the line right there. Okay, so we are looking for the shortest distance between the circle and the line. Now, if this is true that this is the circle and this is the line, this is the distance that we need. Okay, from the line and to the outer edge of our circle. Okay, so this is the distance that we need. But how would we do that? So there are two things that we need. We need this intersection and we need this line, because right now we don't know anything about that yet, whether what are those values or where are those lines located for the case of our given equations right here. So let's do that. Let's try to solve this one by finding all about those. Okay, so in this case it will involve us by trying to remember what are the basic properties now when you talk about perpendicular lines, and probably about the intersections of your two lines. In this case, let's simplify the problem by first converting the given circle into the standard form. In this case, I have now x squared minus 2x, and then that is followed by y squared minus 10y, and then let me put negative 9 on the other side for simplicity. So now I have to complete the square for each of them. Okay, so in order to complete the square, again, you need to look at the second term and divide it by 2, and you square that quotient. Okay, so in this case, I have now x squared minus 2x, and then half of 2, again, divide this by 2, that is 1. So I have here 1 squared. And then for the other side, we have here y squared minus 10y. Divide 10 by 5, that is, sorry, that 10 by 2, that will become 5. So I have to add here plus 5 squared. And then minus 9. And then since I added terms on the left hand side, I have to add them here to keep the equality. So you now have 1 squared and then also plus 5 squared. So compressing each of them to their corresponding binomials, this will become x minus 1. Again, look at the first term and the last term and the sign in the middle. And then we have here y minus 5 squared. Okay, this will become negative 9 plus 1 plus 25, and that is equal to positive 17. Okay, that is now our standard form. So it means that our radius must be equal to the square root of 17, and our center must be located at 1, 5. Okay, let's graph our circle now. Okay, so I'm hoping I can graph this well. But I have this circle. So 1, 5. So let me graph here. 1, 1, 2, 3, 4, and 5. This is the center of our circle, and we have square root of 17 as our radius. I think it would be best if we try to figure out what's the actual value for square root of 17, so that we can have an approximate graph. So that is around 4.123. So let's have just 4.1 instead. So the radius is 4.123. So starting from the center, we need to move 4 units, 4.1 units below. That is 1, 2, 3, 4, and maybe a bit here for 0.1. So it means that our circle should end up right there. Okay, and then in that case, let me draw an approximate circle. Right here, perhaps. Okay, so that is our circle. Now just imagine that is correct. So that is the circle. Now let's graph the given line. According to the given, the line should be located at y is equals to x minus 6. Now, think about this. The slope of this line must be equal to 1, and its y-intercept must be located at negative 6. Okay? So those are the values that we know for this line. So let's look at this. We now have negative 6 as our y-intercept. So we'll count here negative 6 down below the origin. That is 1, 2, 3, 4, 5, and 6. So this will be our starting point if we want to graph the line. And we have a slope of 1. So in this case, it indicates that for every 1 unit change in x, there is a corresponding equal change in y by also 1 unit. So moving to the right by 1 unit, so we move here, it means that y would change by 1 unit also, since m is 1. So this is our second point. Okay, we have 2 points now, so that's it. We can draw the line. Okay, we can connect these 2 points right there. Okay, so let me change this one. Okay, so this now will be the line represented by y is equals to x minus 6. Okay, again, this is the line represented by our circle. Let me just put this standard form right there. Go to 70. So what we need actually, unlike before in our illustration, we now have a more accurate representation of the distance that we want. We want the distance tracing along this path right here. Okay, we need this distance. Let's call that d perhaps. Okay, so first we need to find this point. We need to find this point in order to use the distance formula now for this location right here. Now, think about this. One strategy that we can make is first to measure the distance of this center down to this line, right? We can do that. Again, the way we do that is if we find this point. If you can find this point located at some value of x and y, we can measure this distance from that point to the center and then subtract the radius of the circle. Okay? If this is the whole distance now, let's call this distance big R perhaps. Okay? If the distance of our center down to this unknown point, let's call that R, and the distance of this point right here in the outer edge of our circle is obviously just the radius, then the remaining distance is d. So in this case, d is just equal to r minus r. But in order to proceed with that, we need to find the point xy. In order to find that, we need to find the intersection of two lines. Okay, what are those two lines? We already have one of the lines, that is the given line. But what is the second line? Now, the second line is perhaps a bit obvious now. It's the line passing through the center of our circle and is perpendicular to the given line. So, therefore, it must be this line right here. Okay, that line right there. So again, it's connecting the dashed line right there. So let's find the equation of that line. We know that this is the equation in the first one, but what is the equation of this line right here, the perpendicular line? So first, when we say perpendicular, so it means that the slope of this line is m perpendicular. It should be negative reciprocal of the initial reference line. So in this case, -1, and then the slope of the previous one is m. So that is m equal to 1, or that is just equal to -1. So the slope of the perpendicular line must equal to -1. Now, how can we construct this line? We need at least one point where we know that line must pass through. And that point is the center of our circle, located at 1, 5. So we have an idea now. It's the slope of that line is -1, and it must pass through 1, 5. Okay? And if that's the case, we have to use what we call the point slope form of the line. Again, remember, the point slope form of our line is given by y minus y sub 1 equals to m times x minus x sub 1, where x sub 1, y sub 1 is a point we know, or we are sure, where our line would pass through. In this case, our x sub 1 and y sub 1 would correspond to the location of the center of our circle. Again, that is because we know that the line must pass through the center of that circle. So now have x sub 1 as 1 and y sub 1 as 5. So constructing the point slope form, we now have y minus 5. And then remember, m here would be the slope of the perpendicular line. So that will be -1. And x minus x sub 1 is 1. Now simplifying, this will become y minus 5 negative x plus 1. Transposing to the other side, this will become minus x. Then 1 plus 5, that will become positive 6. So therefore, the equation of this line is y equal to -x plus 6. Now this is a lot similar than the previous one. It just flipped its signs to be on the other side. Now, in order to find the intersection of those two lines, remember, I've tasked you to study in advance about the intersections of our lines. All we need to do now is to get the common values for x and y, such that we can call it an intersection. And the way to do that is to eliminate one of the variables for both of the lines and figure out what is the remaining value for the value that we chose not to eliminate. In this case, I have now y equal to x minus 6, and the other one is y equal to -x plus 6. What we can do is probably subtract the two lines right here, to the two equations right there, so that we can eliminate y. So y minus y is 0. X minus -x, that will become x plus x instead. That will become 2x. -6 minus -6, that will become minus 12. So in this case now, x must be equal to, if you look at this, x must be equal to 6, positive 6. Okay? Now in order to find y, we just substitute this to any of the equations above, any of these two. Okay? So I'm gonna choose the first one, since it's a simple one. So now we have here y is equals to 6 minus 6. Therefore, the corresponding y value of the intersection is 0. So the intersection now is located at 6, 0. Now, my drawing is off. This intersection should be located down below. I'm just gonna draw the label here, 6, 0. Okay, again, the real drawing must have this point down below right here. The thing is, we do not know that yet, so our drawing would be really inaccurate if that's the case. But then just remember that the intersection must be at 6, 0. Okay, now that we found 6, 0, we need to find big R. Okay, we need to find big R right there. And that big R is just the distance between the center at 1, 5 and the point of intersection 6, 0. Okay, so in that case, we now have, let's call this point 1, let's call this point 2. So now I have 1 minus 6 squared plus 5 minus 0 squared. In this case, it will become, we have here 1 minus 6, that is negative 5 squared, and we have 5 minus 0, that is still 5 squared. And this will become square root of 25 plus 25, or square root of 50. Okay, we have that big R right there. So in order to find the distance, all we need to, again, is to subtract the radius of our circle. And we know that the radius earlier is equal to square root of 17. So really, our distance is just big R minus R, and that is square root of 50 minus square root of 17, and that is around the value of, so let me check, what's the value of that? Okay, that is around 2.948 units. Okay, so that's the distance right here. This distance right here is around 2.948 units. Okay, so that is for question number 1. Okay, notice it's taking a lot of time at this point, but when you're solving, not explaining, it would really be a lot quicker for you this way. Okay, now let's move on to example number 2. For example number 2, we have here this question, so let me paste it here. Okay, it says that we have a circle at the center at 3, 4, with a radius of 2 units, was made to rotate clockwise about the origin until its center lies in the x-axis. Okay, so you might ask now, how do we do that? How do we figure out what's happening in that case? Okay, so let's draw the circle. Really, it's just a matter of locating the new center. Much like one of the question in multiple choice there, we're moving the center. In this case, it's a lot the same, only that now we are rotating the center in order to be located at a new point. So in this case, let me graph 3, 4. That is 1, 2, 3, and then we'll have here 1, 2, 3, and 4. So that is the center of our circle, and the radius is 2 units, so we have to move on 2 units here and 2 units above. So the circle is like this, approximately like this. Okay, so let me practice some more. Usually some apps have a utility in order to draw a circle, but again, I'm new to this, so I'm just trying to draw it by hand this time. Maybe I will learn it next time. Okay, now this is our circle. We have a radius of 2, and its center is at 3, 4. Now, what it says is that we need to rotate the circle about the origin such that its center is now at the x-axis. But remember what direction it is. Is it? We have here clockwise direction. So therefore, again, we are rotating about the origin, not about the center. So if we connect a line right here, that is our radius of rotation. If we want it to rotate clockwise, it must go in this direction. Okay? Such that this center should lie in the positive x-axis. Again, it's positive because we are going clockwise. Okay? Remember, it's until the center lies at the x-axis. In this case, if you rotate it this way, the center now would have to lie right here. Again, positive x-axis. So this is the new location of our center. But the radius will not change because there were no conditions given in our question that we should change the radius. So therefore, the same thing, we just need to draw the radius here, about right here, and then about right here. I'm just gonna draw a crude graph again on how would that circle look like. Okay, so our task now is to find the equation of this new circle. Now, all we know is that this distance right here, let's call this big R again, must be the same distance from the origin with the center, from the center of the new circle. That's what we know. Again, when we are rotating, we're not moving the point closer to the point of rotation, but rather we are just moving, circling around it. No, we're not approaching it closer. So therefore, that big R right there must be the same for both cases. So all we really need is to figure out how to find that value of the big R. But that is easily done when we consider that we can just either draw a triangle or do the distance formula. In this case, I prefer drawing the right triangle right here because it's a lot obvious when you do that. Okay, this is the origin right here. This is big R, and in order to reach this point in the center, we need to move 3 units, and we need to move 4 units right here. Again, this 4, so it looks like -1 right now. So let me fix that one. This is 3, 4. Okay, so now R must just be the hypotenuse of this triangle. So R is just really that is just 3 squared plus 4 squared. In this case, that is 9 plus 16 or 25, or R is just equal to 5. Okay, so since R equals to 5, we have that. Now, if you don't want this approach using Pythagorean theorem, you can use the distance formula, but then again, you will find out that you will arrive at the same value with just lesser steps. Okay, so now just say here that R is equals to 5, R is equals to 5. But if R is equals to 5 and it's completely at the x-axis, this location now must be 5 units away from the origin, and the y value must be 0. So therefore, that is the new center of this circle. New center, but the same radius. R is equals to 2. In this case, we now construct the standard form. Again, the new center lies at 5, 0, and its radius is 2. So therefore, the standard form will become x minus 5 squared plus y minus 0 squared equals to r squared, that is 2 squared. So now we'll have x minus 5 squared plus y squared is equal to 4. And since the question is asking the standard form, then we'll have that. This is our answer for that question right there. Okay, so that's it for question number 2. This is a lot easier. It's just a matter of figuring out what will happen if you rotate about the origin. Okay, so that's question number 2. For question number 3, let's move on. Let me copy again the question from the other panel here. Okay, so we have here a circle has an area of 81 pi units squared and is tangent to the x and y axis. If its center is located at the 4th quadrant, determine the equation representing the said circle. Okay, so let's have this. Let's draw where the circle would be located. It says here, center is located at the 4th quadrant. Remember, this is Q1, this is Q2, this is Q3, and this is Q4. So the center must be located within here. And the requirement is that the circle must be tangent to the x and y axis. So it must touch the x-axis and the y-axis at only one point. So there could be a lot of circles, but let's draw one of them. Could be this circle right here. Again, the point is that it would only intersect the x and y axis at most a single point only. Okay, so in this case, let me draw some point of tangency. Let's just estimate that there are actual points of tangency right there. So that is a candidate circle that we have. Okay, the circle should be located in there. Now notice this one. Okay, let me move the point here and secure the center. Let me move the center right here. This one, for some reason that you'll find out later on. Now, if that is the case, if it's tangent to both x and y axis, its distance from this point now must just be the radius of the circle. Okay, it's just the radius of there. So therefore, the center of this circle must be located at positive r units, since we are moving to the right, but negative r units down below, because again, we are at the 4th quadrant. Any y values in the 4th quadrant is negative. So that is the location of our center. So all that remains now is to find the value of your radius. And that's where the area comes in. We have an area of 81 pi units. Okay, so the area of our circle is said to be 81 pi units squared. But remember, the area of a circle is given by the formula pi r squared. So in that's the case, pi r squared therefore must be equal to 81 pi. Now we have the same terms on both sides. We have pi and we have pi. Here we can cancel that. So we are left with r squared is equals to 81. Now taking the square root of both sides, we found out that r is just equal to 9. So what this means is that our center is located at 9, negative 9, with a radius of 9. So since it wants our answer to be in general form, we need first to create the standard form and convert it to general form. So the standard form now is x minus 9, since it's positive, squared, and then y plus 9 squared. And then r squared, that is 9 squared. Simplifying, to become in general form, this will become x squared minus twice of 9, that is 18x, plus 81, and then plus y squared plus 18y plus 81, and then 81. Since you have two 81s here, let's just cancel them both, and this will be equal to 0 and 0. This will become now x squared plus y squared minus 18x plus 18y, and then plus 81 equal to 0. Again, we have only a remaining 81 for our constants, since two of them will cancel out. So this will be now the answer for question number 3. Okay, so that's it for question number 3. Okay, that's it. For question number 4, let's move on to question number 4. We have this one right here. There are two circles given by those equations right there. X squared plus y squared plus 6x plus my plus 49 equal to 0. And the other one is x squared plus y squared minus 10x plus my plus 81 equal to 0. Find the distance between the centers of each circles. Now, this question might seem intimidating because of the two inequalities right here. You'll find out why we have those inequalities later on. Okay? But look at this. All we really need to do now for this kind of question is to try to see what will happen if we want to measure the distances between their centers. So in order to do that, we must find first the location of the center for each of the circle. Although we have a variable m, let's just assume now that that has a certain value right there. So in this case now, let's convert the first equation, x squared plus y squared plus 6x plus my. Sorry, that's plus 49. Okay, let's convert this to the standard form. Now, in order to convert to the standard form, all we need to is to graph the terms. To group the terms rather. Now, in this case, I have now y squared plus my, and put negative 49 on the other side. In this case, we figure out what do we need to do or to add to each of the terms. In this case, I'll add here x squared plus 6x, and then I'll add here 6 divided by 2, that is 3. So therefore, I'll need to add 3 squared. And the other one, I have here y squared plus my. So since m is a variable, I have to divide it by 2 but keep its form. No, so this will become now m over 2 and then square that one. That's what I will add. And I have here negative 49. Okay, so what's happening here? And then I'll add the terms that I added on the other side. This will become 3 squared, so that is 9. And then we have here plus m over 2 squared. Okay, completing the squares or converting this to the binomial forms, this will become x plus 3 squared. Okay, and then plus y plus m over 2 squared. Okay, now simplifying, this is m over 2 squared minus 40, I believe so. Okay, so therefore we know that the center of this one is at 3, negative 3, and negative m over 2. and its radius is equal to the square root of m over 2 squared minus 40. We have that going on for us. Now, for the other circle, we have here x squared plus y squared minus 10x plus my plus 81 equal to 0. Let's group again the terms. This will become x squared minus 10x, and then you have here y squared plus my, and then transpose 81 to the other side. This will become negative 81. And then add the terms that we need. So in this case, I'll add half of 10 squared. So that is 5 squared. Then for the other one, I'll add the same, like the first circle. So my plus m over 2 squared minus 81, and add the same on the other side. So 5 squared is 25, and add here m over 2 squared. Okay, now let's look at this. We now have this one right here. Condense this to binomial form. This will become x minus 5 squared, and then I'll have here y plus m over 2 squared. That is equal to negative 81 plus 25, that is negative 56, plus m over 2 squared. So now we know that the center of this one is located at positive 5, negative m over 2, and its radius is equal to the square root of m over 2 squared minus 56. Okay, we have two centers now. In order to find the distance, again, from center 1 and center, let's call this center 1. Let's call this center 2, or circle 1 and circle 2. In order to find their distance, basically we just use the distance formula. Okay, distance formula from C1 to C2. In this case, let's call this point 1 and point 2 so will not be confused. So in this case, point 1, that is negative 3 plus, minus 5 squared, and plus m. Okay, so we have here negative m over 2 minus negative, so that will become positive squared. So now notice this term right here will just become 0. Again, we're subtracting the same y value for each of them. So that's just negative m over 2 minus negative m over 2. So the other one will have to be positive. Notice this will become 0. So all we have left is a constant value right there. Okay, now that is negative 3 minus 95, that is negative 8 squared, or that is just the same as 8 squared technically, or if you want, that is 8. Okay, that is, I'm sorry. Okay, so that is the same as positive 8 squared technically. We have negative sign there, so it's just the same. Since we have a square root and a square there, this is gonna be equal to 8. Okay, so now that's the distance between the two centers of those circles. Okay, basically it doesn't matter now that it has a variable m in the general form of these circles. What it means that for any value of m, you would just be changing the radius of the circle, but it will not affect the relative distance between the two. It would not affect the relative distance between the centers of the circle. Now, the centers of the circle could move up and down, but it should maintain, or both of the circles should maintain the same distance away from each other as they move up and down. Okay, why do I say that the movement is up and down? Notice that our x coordinates are fixed at constant values, while our y coordinates are free to move depending on the value of m. So for example, m is 50, then our y location will be at negative 25, negative 25. Or if 100, if m is 100, then the location of the y coordinates for both of the circle is at negative 50 and negative 50. Because again, we have m over 2 and m over 2 for both of them. So the circles will have to change radius. Right there, it could move downwards right there with lot larger radius. But again, their distances from each other must remain equal. So at all times, those distances must be equal. You could have a circle, another right here, another right here. Their distances must be always equal to 8. Okay, so we have 8 and in between each of them, depending on the m value right there. Okay, now you might notice we have these inequalities right here, right there. What it really means is that it's a restriction on the radius of the circles. So if you look at this, which of the circles now, or for circles 1 and 2, we have to look at this, that one of them will have to be invalid first, depending on the value of m. And in this case, I believe so, it's the 56 minus 56 radius that will have an m. Okay, notice that the subtraction here is a lot larger than minus 40 on the other side. So this will approach fast into an invalid value based on the value of m. So in this case, remember, we want this radius to be greater than 0 for it to be a circle. Otherwise, it's not a circle anymore. So therefore, we need square root of m over 2 squared minus 56 to be greater than 0. Now that is the same case here. We need this to be greater than 0. But we will find out that this one is at risk of being invalid faster, since this subtraction here is a lot larger than 40. So following that idea, we can just square both sides and figure out that we have now m over 2 squared minus 56 greater than 0. Okay, now let's transpose 156 on the other side. You can just transpose this in your inequalities, and then this will become positive. Again, the same property. And then perhaps let us maybe let's take the square root of both sides. Okay, in that case, now if we take the square root of both sides, we'll have m over 2, but we don't know the equality sign here because we now have plus minus square root of 56 right there. And I believe square root of 56, that is the one that we saw earlier. That is 2 square root of 14 rather. So we have m over 2. We don't know the inequality sign yet, but we know that it's 2 plus minus square root of 14. So in that case, now we have to go on and try to see whether this will be, which of the m values later on will have to be the case. Should it be greater than or less than the positive or the negative values, such that this is valid. And you will find out later on that the truth is that if we have here m is equals to, okay, remember we have a sign here, I can just get rid of 2 over 2 here. I have an unknown sign here, plus minus 2 right here. I can multiply 2 on both sides. That would still work. And I'll have now m with some unknown signs and plus minus 4 square root of 14. But what you'll find out later on, that the truth is that m should be greater than 4 square root of 14, and m should be less than negative 4 square root of 14. Again, we have this plus minus. Now, that is because if this is followed, then this inequality right here will be true. Okay? So that's just the reasoning there. So basically, if you go on into your general mathematics, all you need to do now is to provide some test points for that. But that's beyond the scope of our discussion. So right now, just think of it that those inequalities now, make sure that these equations are still circles, meaning their radius are greater than 0. Okay? But the important thing here is we have found the distance between them. Again, the distance is constant and is equal to 8. For it to be constant, the two circles must just be moving up and down with changing radius perhaps. But they should maintain the same horizontal distance away from each other. Okay? So that's it for question number 4. Now, for question number 5, this is an application of one of the multiple choice question. This is a bonus question. Sure, you are not really required to solve this one, but if you did, I would really commend it. That action. And I don't think anyone has solved this one on the previous exam, but this one is really a good problem, if you'd ask me. Okay, because it would apply the properties of our chords and perhaps the lesson that I've tried to let you study in advance, which is about the uh, intersection of your lines. Okay, so again, we start with graphing the known values right here. So the only known values right there are the 3 points on your circle. We have here 1, 3, 2, 2, and 5, 1. So in order to do that, let me create first the xy plane. Okay, so we have this xy plane right here. And we have 1, 3, so let's graph that. 1, 2, 3, I have up to 5, so I'm just going to graph ahead of there. 1, 2, 3, 4, 5, and have the highest value of 3, so I'm just going to go to 3. 1, 2, and 3. Okay, so let me graph the first point, but let me change colors first. That is 1, 3, this point right here, and the other point is at 2, 2. So this point right here, that's 2, 2, and then the other point 5, 1. So somewhere around here. Okay, now these 3 points now must belong to the same circle. Now, if you look at this, remember that the properties of our circle is that it should only locate one circle if you're given 3 points, as long as those 3 points are not collinear. Again, it was exhibited on one of the multiple choice questions earlier, so please look into that as to why there's only one possible circle for the given 3 points right here. Now, if you look at the curvature, it seems like the circle is along the upwards direction. So if we trace the circle here, it could be this circle right there. Okay, we have this circle right here. I'm not really sure how it would look like, but probably this way. Okay, but because the curvature is towards that direction. If perhaps this second point is somewhere along here, then the circle will have to be pointed, or will have to grow on the other side of these 3 points right there. But for now, the curvature is facing upwards, or perhaps upwards, somewhat kind of upwards, diagonally upwards. Okay. Now, remember, let's recall the properties of your chords. We can make a chord here. This is one chord up to this point. Okay, this chord right here, and another chord right here. Again, I can use the other chord right here, but I prefer the 2 values right there. So let's use them. Okay, we have a chord there, so let me take one of the chords. We have a chord at 1, 3, and 2, 2. It's this chord, and the other chord is this at 5, 1. So it must be a little lower there. This is at 5, 1. So I'm just drawing an enlarged image so that we can we can better analyze the problem this way. Okay, this is the second chord. Again, it's a chord because it intersects the circle at twice, or 2 points. Okay, now, according to the properties of your chords, it must contain the center, or the perpendicular bisector of chords must contain the center of our circle. So therefore, if this is the perpendicular bisector for the first chord, and the other chord has this perpendicular bisector, again, these are lines, so those are not line segments, meaning they don't have endpoints right there. Okay, let me try to recreate this one. Okay, these are the perpendicular bisectors, hopefully. Okay, we have this perpendicular bisectors, meaning they are perpendicular to the line segments right here. So at this point, this should be the center of your circle. So the problem really now boils down into finding just two perpendicular bisectors, find their equations, and find their intersection, so that we can find the center of this circle. Okay, so in this case, we need to figure out the slope. Let's call this slope 1 and slope 2. Okay, we need to find those slopes. In doing so, we can then construct later on the perpendicular bisectors. Okay, let's solve for slope 1. Now slope 1 is just, again, slope is just given by the changes in y divided by the changes in x. When you say change, it's just a matter of subtraction. So subtract the y coordinates and subtract the x coordinates. The choice of which point you want to be the first point and the second point is really arbitrary. It means that you will get the same answer even if you switch the positions. So in this case, consider this point 1, 3 as the first point and the second point 2, 2 as the second point. So therefore, our delta y, or the change in y, will just be 3 minus 2, and change in x will be just 1 minus 2. In this case, m1 is just equal to 3 minus 2, that is 1. Negative 1 minus 2 is negative 1. So therefore, m1 is really just negative 1. Now it should be negative because notice how our line segment is oriented towards in respect to the origin, or in respect to the x-axis. Notice it's going down on the x-axis as our x value increases. Okay, now without much further conversations regarding this one, let's solve for m2. Same thing, we just need to remember delta y divided by delta x, that is the changes in y divided by the changes in x. Okay, for this purpose, let's call the point 22 as our first point and 0.51 as our second point. In this case, our equation will become changes in y, so this will be 2 minus 1 and 2 minus 5. In this case, m2 is a lot smaller slope because, again, look at how inclined it is compared to m1. A lot smaller in terms of magnitude, but since one is more negative than the other. Okay, so now we have 2 minus 1, that is positive 1, but 2 minus 5 is negative 3. So therefore, this slope is just negative 1/3. Okay, so m2 is negative 1/3. Okay, now we wish to construct those lines right here. Okay, this is just a replica. This one right here are just replicas of the smaller chords in the figure. We want these lines right here, and we want this other line right here. So I cannot draw anymore where it will cross each other, but you get the idea that those two lines are the same. Now let's call the slope of this one mp1, and let's call this mp2, meaning they are perpendicular slopes than their reference slopes. So mp1 must be the negative reciprocal of m1. In this case, that is negative 1 over m1 is negative 1. So mp1 therefore must be equal to positive 1. Now for mp2, we have here mp2, that is just the negative reciprocal of m2. So mp2 right there must be equal to negative 1 over negative 1/3. But you're dividing with a fraction, so it means that you're just multiplying with its reciprocal. So negative 1/3 over 1. So those are two the same thing. So mp2 therefore must be negative 1 times negative 3 over 1, or that is positive 3. Notice it agrees with our observation that both slopes must be positive. Okay, they should be positive since you look at the orientation, they're obviously in a positive state. Now we have the two slopes. Now we need a certain point that we know our lines would pass through. Now that could be the center, but at this point the center is unknown. So what are the known points available to us? Now, since these two lines are perpendicular bisectors, it means that it must pass through the middle of the line segments. When you say middle of line segments, it's basically their midpoints. Okay, so the midpoints of this line this line segments right here are where we are sure our perpendicular bisectors would pass through. So for example, for segment 1, where we have m1 located at, the slope, the midpoint there is just the average. Again, our midpoints are just averages of the coordinates for two points. Okay, in this case, the midpoint there is just average of x, so that is 2 plus 1 divided by 2, and the average of y, that is 2, and then we have y coordinate of 3 for the first point. Okay, it doesn't matter what's the order because you're just adding. So 2 plus 1, okay, so that is 3 over 2, that is 3 halves. And for the other one, that is 5 over 2, that is 5 halves. So I'm not going to simplify that. Those are the midpoint. So meaning that the midpoint here is located at 3 halves, and the midpoint here, it's located at 3 halves, 5 halves. Now for the other one, the midpoint is just the same. We're just solving for a midpoint again. Okay, this is segment 1. Or rather, let's call this chord 1 and chord 2. Okay, this is chord 1 and this is chord 2. Okay, now for the midpoint of that one, we're just averaging again the x coordinate and the y coordinates. We have now, let's start with the first one. We have 2 plus 5 over 2, and we have here 2 plus 1 over 2. So the midpoint must be at 7 over 2, and the other one must be at 3 over 2. So the location of this is again at 7 over 2 and 3 over 2. Now we have the points and we have the slopes. So all we need to do now is to use the point slope form in order to construct the lines. So again, let me summarize the values that we know. For chord 1 and for chord 2, we know that it must pass through the point 3 halves and 5 halves for chord 1, and the perpendicular slope there is 1. Now for chord 2, it must pass through the point 7, 2 and 3 halves, and it has a slope MP2, which is equal to positive 3. Now constructing of this perpendicular bisectors is really an easy task. You just use the point slope form. In this case, we have now y minus y sub 1 equals to m times x minus x sub 1. Our x sub 1 and y sub 1 will just be the midpoint themselves. So y sub 1 there will become 5 halves, and then m is positive 1, and then x minus x sub 1, or 3 halves in this case. Simplifying, this will become, okay, we can multiply both sides by 2, but I will just prefer now that we have y equal to something in the form that we recognize. Okay, so now this will become x minus 3 halves plus 5 halves. Okay, in this case we'll now have x minus, since those two have the same denominators, this will just become negative 3 plus 5, or that will become 2 over 2. In this case we have x plus 1. This is the equation now of this perpendicular bisector here. Okay, this x plus 1. Now for the other perpendicular bisector, you just use the same method. You have now y minus y sub 1 equals to m times x minus x sub 1. We have y sub 1 is equals to 3 halves, and then we have m is equals to 3, and then x minus 7 halves. Okay, simplifying, we now have 3x minus, this will become 21 over 2, and then plus 3 over 2. Okay, this is 3x. Now 21 minus negative 21 plus 3, that will become negative 18. I think so. That will become negative 18 over 2. And then this will become 3x. And then 18 divided by 2 is a whole number, that is negative 9. So now that will be the equation of the other perpendicular bisector. So the equation here will be 3x, y equal to 3x minus 9. Okay, now remember, the center is the intersection of those two lines. By now, we should know how to solve for the intersection of our circles. So really, we just need to intersect y equal to x plus 1 and y is equals to 3x minus 9. And in order to do so, we just need to eliminate one of the variable and figure out what's left. So let's try subtraction this time. Again, there are many methods. You can equate both equations, but I want here to use subtraction. Okay, you can subtract the equations. In this case, y minus y is 0, so we have eliminated y. Now we have x minus 3x, that is negative 2x. 1 minus negative 9, that is positive 10. So therefore, x must be equal to 5. Okay, you can simplify this one and you can solve that. It's x is equals to 5. Now to figure out y, you just substitute into any of the equations right there. In this case, I'm going to choose the first one. So I have now x equal to 5 plus 1. So its corresponding y value must be 6. Okay, now this is the intersection of those two lines right here, 5, 6. If that's the case now, that is our center. Okay, that is the center of that circle. So we now have the center at 5, 6. Now we lack the radius of that circle. So how do you find the radius? Now basically, in order to find the radius, you just need any of the 3 points, the distance from the center and then to any of the 3 points, because again, those 3 points lie at the circle itself. So any distances now from any of them down to the center would give us the radius. In this case, let us choose the 0.51. So let's measure our radius. Our radius now is our center 5, 6 to 5, 1. Okay, so our radius will be given by the square root of, so let's just call this 0.1, let's call this 0.2. So in this case, it will be 5 minus 5 squared plus 6 minus 1 squared. That is, now this becomes 0. But we have here 5 minus 1, that is 6 minus 1 rather, that will become 5 squared. Since we have squared and a square root, this will cancel out and we'll have a radius of 5. So now we all have what we need in order to construct the circle. We have the center at 5, 6, and we know that the radius is 5. So let's go back above. We have now the radius is equal to 5. Now, if that's the case, we can now construct the standard form. According to the standard form, we have now x minus h squared plus y minus k squared is equals to r squared. In this case, h will be equal to 5, and then k will be equal to 6. And then r is equals to 5. So let's substitute all the values now, and we get the standard form. X minus 5 squared plus y minus 6 squared, and then 5 squared, or just 25. That is now our equation of this circle right here. Okay, the circle has an equation of x minus 5 squared plus y minus 6 squared is equals to 25. Okay, that's it. Basically, that's all of the problems for exam 2. So follow along this discussion. Maybe this would appear again on your quarterly exams, but what I suggest is to focus more on the analysis rather than memorization of formulas, because I believe so that's what you lack based on my observations in your last exams. So try to be more analytic about your solutions. Try to figure out what the problem is saying, and do not forget to learn the basics of basic operations, like even integer operations, the fraction manipulations. You can use your calculator for that, intersections of your lines, and etc. But for now, let's end our discussion, and I hope you learned something. Goodbye.